recording from my side. You guys have received the handouts of 3 pages of a grounding and bonding system. You're looking at it right here. Should be 3 pages. And the other thing, I gave you also a handouts of a PowerPoint presentation, which looks something like this. So everybody got that? We're clear? What I'm going to start, guys, is I'm going to start with actually talk a little bit about the grounding and bonding, and then we'll go to the example. So let me go right here into this and start. Let me go back into right here. To help me with this, guys, and as a resource for you, being an engineer, IEEE 142 talks intensively about grounding and bonding. So if anybody wants more resources about which system need to be grounded, which system can be ungrounded, need to be impedance grounding, that's a great resource for all engineers. Then we have the source book right here. These pictures are taken from it. It takes the IEEE standard down to earth and puts it in pictures, or some of it, not all of it. So that's what I thought for you for grounding and bonding. The idea here is to ground. There are 2 types of grounding, or at least 2 concepts of grounding. The concept number 1 is ground the system. So you take a system, you guys don't do a whole lot of single phase. The most important system that we use is a grounded system, solidly grounded system. Right here, it's a Y. They call it Y4 wire system. That's when you get to 123 phase system and 480 277 system. So the first thing is grounded the system. You can see they take a wire down to the guts of the winding of the transformer or the generator, and they tie it directly to Mother Earth through the grounding electrode conductor and the grounding electrode system. That's what the concept of grounded system is. That's one system. I don't know if you guys use center tap delta. This system is also another grounded system, 3-phase center tap delta. Take one winding of the transformer or part of the winding and you tie it directly to Mother Earth through grounding electrode conductor. And these are 2 single-phase systems. This is the most commonly one. I don't think you guys use a whole lot of 24120. Most of what you use is 480 When we ground the system itself, when we ground the system to stabilize the voltage to the ground, so you can get yourself 277 or 120 between this neutral conductor and any other conductor. Same thing here, you get yourself 120 between these 2 phases and the neutral. So that's concept number 1 for grounding. Concept number 2, stabilize the voltage to the ground and get rid of all transient voltages that the system might encounter. So if you have a grounded system, your chances of getting transient voltages, suppress the transient voltages, is much higher than if your system is ungrounded. So that's what I want to start. You're looking at ungrounded system. When I was green years ago, the most confusing thing was for me is the difference between grounding the equipment and grounding the system. All electrical equipment, with some exception, must be grounded. The equipment, the boxes, the transformer box, the panels, the switchgear, the switchboard, the MCCs, these have to be grounded. The systems, you have a choice between grounding the system or not grounding the system. You're looking here at a system that grounded system right here, and you're looking here at a system that's ungrounded system. Typically Delta, though Y can do a business of ungrounded. Here's all the voltages that we use. Dave, do you guys use a lot of ungrounded system? 483 phase, assembly lines. The advantage of running an ungrounded system, if you have an assembly line and you're taking a cow from this side and can't beat from the other side, is that too graphic? Or a steel from here, an F50 for the truck from the other side, and you want the assembly line to continue to work if you have a ground fault on it, an ungrounded system will be an ideal situation for you for the most part. So these are the voltages: 240, 480, 2300, 46, and 1380. We run them ungrounded system. I don't know if you guys run any of these ungrounded systems. So that's, I thought, just to start with first, the difference between the system can be grounded. When we say grounded system, we talk about the winding of the transformer has to be tied to the ground, not the box, not the frames. So these are the 2 systems, the grounded and ungrounded. There's something in between. I'm going to go directly into the system in between. There's also, to take advantage of a grounded system, fully, you're looking at what's so-called what IEEE 142 calls it solidly grounded system. That's the most common one here. You get 122.77 voltage from it.
You can also have another one that's the ungrounded system that we looked at, or something called reactance or impedance grounded system. So the grounded system will get you a voltage to ground, stabilize the voltage to the ground, and get rid of the transient. Ungrounded system gets you survivability of the system. So if you have the first hit, you're still standing, meaning the first ground fault, you're still standing, the system is up and running. The second ground fault will get you down. That's ungrounded system. The one that we use in between here is called impedance grounded, either reactance or resistance. That guy gives you the advantage, almost the advantage of both systems. So get your stability to the ground and getting rid of the transient, and at the same time survivability. If you have the first ground fault, you will be able to monitor that ground fault and trip if needed. So that's, I thought, this is the start point. All these graphics, guys, and pictures, I encourage you to have one of these. I don't know if you guys have one of these books here. All the graphics are in there. Great resource in terms of explanation. So here's the ungrounded system. The grounded system can be resistance, high resistance or low resistance, or can be ungrounded. But the most common system, what we call it, is the grounded, solidly grounded system. Solidly grounded system, ungrounded system, or impedance grounded system. All these in Article 240 as well as in IEEE 142 and the source book. Any comments, guys, before we go talk about grounding the system? The advantage of grounding the system is getting you a voltage and stabilize the voltage to the ground and get rid of the transient. Transient coming out of lightning hitting the transmission line, or an air handling unit switching on and off and making transient into your voltage system, into your power system. So I thought I'm going to start with these, if you guys don't mind, and I'm going to go then. Now that we know what the system, at least explain what the system can be grounded and not. So the system, we have to decide if we want to ground a system or not, based on the application of that system. I dare to say 90% of the system that we run are solidly grounded in the 480, 277 systems. If you go higher than 480, 13.8, 4160, then it becomes they run a lot of impedance grounded or ungrounded system. A lot of impedance grounded. Okay. Any comments, guys, corrections? You're familiar with these systems. Anybody has any inputs before we move into grounding the equipment? Now what we talked about right now is the system, meaning the windings of the transformers or the generators. Part of that winding is intentionally connected to the ground. That's what grounding the system is. Now moving into grounding the equipment. Grounding the equipment, with very few exceptions, all equipment must be grounded. Meaning if you have anything metallic that contain anything electrical, higher than 50 volt, that metallic object, metallic box that you have that houses a transformer or a panel or an MCC or a magnetic starter or a disconnect must be grounded, with very few exceptions. So I thought to start with when you start very simple system, and then I'll go into the sizing. You came up with, here's a single phase, which very similar to a three phase. You started with a grounded system. You can see here, given to you by the utility, by connecting part of the transformer into the mother earth, stabilizing it. Then they give you a neutral, that's called grounded conductor, that the code considered the neutral grounded conductor. So I am bringing a grounded system into my building. Then, right inside my building here, I need to establish my grounding electrode system, what they call a grounding electrode system. So what they do here, right here, they grab the grounding bar inside the panel and they pull a conductor, which is called C conductor. This is a grounding electrode conductor. When I start using the NEC code book, guys, one of the most confusing ones, if you're confused with the grounding bonding, is the terminology that they use. There's a difference between a grounded conductor and a grounding electrode conductor, an equipment grounding conductor, an equipment bonding jumper supply side, and supply side bonding jumper, and main bonding jumper, and system bonding jumper. All these terminology, the NEC code book, throw it all over. If you don't understand what they are and where they're used, you get always confused when you deal with them. So what I did, I took all these and put them in one sheet for you. You look at the sheet that we're going to go over, with definition, defining every single one of them, and where in the NEC code book is located. That term, where is it in the NEC code book is located. So I want to start with you bring Here's your grounding bar inside your panel. You grab something called grounding electrode conductor and you tie it to the steel of the building. A ground rod, a water. That's the NEC code book called them the grounding electrode systems here. Then we have, so that's my grounding. I'm grounding the equipment here, the service equipment. I'm grounding it. Then you go into the air handling unit here. You can see that this could be my air handling unit or exhaust fan, and I'm pulling an equipment grounding conductor. They call it equipment grounding conductor. That's to ground the frame of the air handling unit, not the windings of the air handling unit. Right? The air handling unit is typically a Y a motor, three-phase motor. So you don't tie anything to the windings. You tie to the frame of this air handling unit, rooftop unit, chillers, you name it. So that's called that conductor right in here. This is called equipment grounding conductor. You can also use, instead of an equipment grounding conductor, you can use any metallic conduit system approved by the NEC code book, as in electrical, metallic, EMT, rigid, intermediate, and a bunch of other ones that approved as so-called equipment grounding conductor. So what we do is we ground the frame here, we ground the frame of this box, and also we ground the frame of this sub-panel to the main sub-panel. That's called grounding the equipment. Grounding the equipment. So have I established the difference between grounding the system and grounding the equipment? All equipment must be grounded. Systems is up to you. Though 90% of the system that we use in for 600 volt or less are grounded system. Very simple here. That's what you guys call it, the ground. When you pull a branch circuit, 20 amp branch circuit to feed a bunch of lights right in here, you pull with it a number 12, typically number 12 equipment grounding conductor. Equipment grounding conductor. So that's the grounding part of the system. The reason why we ground the equipment to put them at the same potential at zero potential ground. So if you're grabbing into one object and another object, you don't have 50 or 60 volt between the right hand and the left hand, which means every time you have a difference in potential between any two objects, what do you have? And you connect them together with a conductive path like my hands. You're going to have a current going right through somebody's heart. So that's the main reason for grounding the object to safety. Safety is the main reason for grounding the object as in the equipment. Any comments, guys?
First panel.
Good. Yes. Now we're coming to this one. So first we grounded the system, which is we're doing it right in here. Then we grounded the equipment, right, which is all the panels, the transformers, the frames of these air handling units, as well as the fans. Then only at the service, you bring grounding the system and grounding the equipment together by bonding them together. And that's what they call it, the main bonding jumper. And you come over here and you bond them. You can see how that little connection here, that little deal is grabbing the system that I'm already grounding it and the equipment that's already grounded, and you put them both at the same potential by bonding them with something called system bonding jumper. System bonding jumper. And we're going to talk about, is that what you mean? Talking about bonding the two systems together. Any comments, guys? Any questions about that one? Yes, sir.
You got the solid grounded, which is just grounding to your ground rod. I understand running through the surge arrestor. The third one, the grounded conductor, what's the benefit of doing that as opposed to just grounding straight to the rod?
I'm coming right here. Yeah. Grounding through a reactor or through a resistor. They call it high impedance grounded. The advantage of grounding the system through a resistor is getting rid of the transient in the system and stabilizing the voltage to the ground. So you cannot get on an impedance grounded system. You don't have the advantage of having voltage to ground. Like in a solidly grounded system, you have a major advantage. You have two voltage systems coming to you, 480 and 277. In an impedance grounded system, the only voltage that you can utilize is the 480. You cannot utilize the 277. But when you put the impedance right here, you basically eliminate the hazard associated with tripping your circuit breaker because of a ground fault. You can monitor any ground fault and decided if you want to act on it at any time. But I guess the major part of it is the survivability of your system. It makes your system more survivable, and at the same time eliminate the transient coming out of ground faults in your building. If you have a ground fault on an ungrounded system, you have a transient voltage that hit the panels, and that transient voltage burned my laptop and your phone right here. If the system is ungrounded, if the system is impedance grounded, you can control that current that going to the ground. Control. When I say control, you control it that you don't trip the circuit breakers, so you don't you interrupt the process of making canned beef from a cow, and at the same time eliminate the hazard associated with the transient coming out of a ground fault. Does that make sense? They use them a lot in a high voltage system. I did a couple of grounding classes, and they are also going into impedance grounding in a low voltage system, just because of the transient. So.
Right, so this is the grounding at your main service transformer. I guess what I'm asking is, don't you know what would be the same as having a transient surge protector at your main panel? What you normally install to protect these transient surge?
Yes. The transient surge protector. Yeah, the surge protective device. It's called surge protective device that you install on a grounded or ungrounded system. So if I have a system like this, and I grab a surge protective device, and you typically bring it from here. You put it right here on the phases, right? And there's another volume here, and you go from here to the ground, if I'm drawing it right. So that will look at the transient that happening on the phase. Here's my phase voltage. So now I have a transient happening because of transmission line going all the way. That's supposed to chop it down by taking it all the way, close these, and taking it to the ground. That's the transient that hit the phase A, phase B, and phase C. Now, that's my understanding is that's not a transient that's happening because of a ground fault. Because of a ground fault. If you have a ground fault on an ungrounded system like this, if you have a ground fault on an ungrounded system like this, there's some transient created because of that ground fault. The impedance will take care of that one for you. I don't know if that makes sense. So there are two different transient. One is coming from a transmission line getting hit by lightning under normal operating condition. The surge protective devices, for the most part, will handle it right there. But if you have an ungrounded system like this, and you have a ground fault, as a result of high impedance to the ground, you create a transient into the voltage system here. And that transient could be very harmful. And the only way you can capture it is two ways. Either you ground the system, one way, which is now, what's wrong with that? You killed the advantage of ungrounded system. If you ground the system, you kill the advantage of grounded system is survivability of the system up on the ground fault. And I hate to make it hard to believe that, but there's the studies that says 85% of your faults are ground faults. Now imagine if you have a system that can eliminate the interruption of your power system. 85% of any interruption that happens in your power system is eliminated by ungrounding the system. Isn't that be great? So meaning if you have a ground fault, which is 85% of your faults are ground faults, you can basically get rid of all these. If you're a factory and you're making assembly line and you're going to make money, interruption of power is a lot of money for companies. So if you can eliminate all this, that's a great system. What's the disadvantage though? Disadvantage, and I've been in a lot of companies where you have, if it's ungrounded and you happen to have a ground fault, it creates a transient that sits in your system and make transient surges, which will burn electronic equipment, not their air handling unit, but the electronic equipment. To take advantage of the two together, they stick that little impedance here, basically, and your system now, the current has to go right through this impedance. Then you have control over the amount of current that you allow to go, which means it will be high enough to be detected and acted upon it whenever you have a break for your electricians on a Sunday when nobody's working. You can go monitor, see where the ground fault, and solve it. And at the same, so that will be monitored high enough to be detected by the monitors, but not too high to trip the circuit breaker and interrupt the flow of energy into your building.
There was a question about the resistance grounding that was, is that the way they do it in Europe?
Resistance grounding, high resistance and low resistance. I don't know what they did in Europe. I grew up in the Middle East, so I can tell you a lot of 90% of the system that we did is a solidly grounded system. It's 220, 380, line to neutral. My sister lives in England, so we have a system, I'm familiar with their system. They use a grounded system. I'm not sure if they use it. In the US, we use resistance grounding, high resistance and low resistance on the high voltage system. That's my experience with it, on 13.8 and 4160. We also use reactance, but I'm not sure. I'm not sure if they use it there or not. But I know we use here in the US reactance and resistance, high and low.
I guess that's the one kind of problems that have the deep grounding, so I think
You spend more time on it. Okay, so yeah, that would be the way. So we can, like I said, guys, what we do, we put 16 hours of training all on grounding. So there's a lot of time we can spend on grounding. So what I thought now, since 95% of you guys are going to be right into this system, and let's go back into, I have my I grounded my system, I grounded my equipment, I tied them together with something called main bonding jumper right in here. So that's what we're going to be talking about: the main bonding jumper, the grounded conductor, the grounding electrode conductor, and the grounding electrode system. Now bonding, here's another system, another nice example of, here's my system is grounded through the utilities. We'll do this grounding system here is done typically by utilities. They bring the neutral to you, then you ground your equipment, and you tie the two together right here, the main bonding jumper, tying the equipment into the neutral, into the grounding electrode conductor. Then you pull 4 wires into the second sub panels, and never again you ground the neutral. Here you can see you ground it one time, the neutral that comes from the system here, grounded. You ground it one time at the service, and then right here, I don't know if you guys can see, there's complete separation between the equipment and the grounded conductor that's coming out of your system. There's bonding. There's the term bonding. Bonding is tying equipments together. And here's my my conduit here, bonded in both sides to the enclosure. A bonding conductor can act as an equipment conductor too, or a bonding conduit can act exactly like as an equipment. So you can have an EMT conduit that bonding 2 equipments together, and at the same time acting as an equipment grounded conductor. So that's what I want to. And then right here at the facilities, you have to create and establish your own grounding electrode system. Because of the time, I'm going to go jump, and I will come back to these guys, but I'm going to jump into the sheet that I have for you. And let's just go directly into, since we mentioned a few things here. Okay, minimize that. All right, so I'm going to cross that one. There you go. Okay, so I thought it's essential to understand a few things about grounding the system versus grounding the equipment. So if you don't mind me walking you through that sheet, I don't know if you guys have enough chance to look at it. What I did is, based on article, let me just show you where this comes, and I really appreciate any feedback. I have been doing this one a lot for electrical contractors when we do grounding and bonding. So here's the article, that Article 250 talk about grounding and bonding. A lot of sections, guys, if you look at this article, it talks about the general grounding. This talks, part 2 talks about system grounding. DC, we're not going to talk about DC today. Grounding of system higher than 1K, we're not going to talk about it. Part 3 talks about grounding electrode system. Enclosures, that's your equipment grounding. at the service. This is your equipment grounding downstream. And this is also methods of equipment grounding, as well as equipment grounding and equipment grounding conductor, these two. And this is all the bonding. You can see the bonding goes with each and every one of them. So that's kind of what I did. I took all, at least my understanding of these, and put them in one sheet for you. So let me minimize this. Okay, so here's how you understand, and I really appreciate, especially the engineers and anyone who is good with the grounding, if you guys critique it and let me know if any mistakes. Okay, here's the assumption. We came up with as high as you can get, 13.8 on the primary side delta and 482.77. This is a typical, say if you have a hospital, a small size hospital, sport arena, well, bigger building, typical application for a building, you take a service of 482.77 coming to the building. This transformer is owned and operated by the electrical utilities. So what they do, you can see this is they call it a 4-wire ground, solidly grounded system, right? So here's my 4-wire coming into my building. They ground the neutral, they tie the neutral to the ground, and they go establish reference by tying it to the Mother Earth via grounding electrode conductor and a ground rod. So all this here is done by electrical utilities. Coming to your building, we're bringing a 4-wire system to my building, right? Typical. This is very typical. From the 4-wire system, you do not bring 5 wires. You do not need a grounding electrode conductor going back to the transformer. From the 4-wire system, you came up with what we call it the CT cabinet or the meter socket, depending how big your system is. Right in here, the code allows you to, so you bring your 3 phases, and the gray here is the grounded, so-called grounded conductor. And what I did, guys, can you see where it's 1.0 here? 1.0. I took it, if you go down here, it says 1.0 grounded conductor neutral at the service. And if you go here, so you know that I did not dream of these numbers. These are where the NDC code book talk about them in 220.61 A, B, and C, and 250.24C1, blah, blah. So these are related to this particular conductor, so-called the grounded conductor, which is a neutral. Right here is the sizing based on, we size it based on power system. Remember how we size a neutral last two times? Not smaller than the main bonding jumper. Your neutral by code, I believe it's somewhere here, says, this will tell you that the neutral cannot, no matter what your size come up with, you can't go smaller than the main bonding jumper. And if you parallel, they cannot be smaller than 1 aught. So what I did is I took every conductor number, here's the name of the conductor, and here's how to size it, and also here's where in the NDC code book says so. What you see, you guys have it colored, right? Everybody has that colored. The red stuff is actually an example. Does that make sense? An example of all. Every time you see that red is an example. Okay, so we came out of here. We came with a grounded conductor into the the meter socket. What we do is we ground the frame of the socket with the neutral. They allow you to use the neutral here to ground the box because you are so-called on the line side of the service disconnect means. So here's my socket. I grounded. Can you guys see that little dot here? This is supposed to tell you that the neutral in the socket, in the meter socket, is tied to the frame, the box. You're grounding the box with a neutral. That's okay with an NDC code book. Then you brought, again, the 4-wire system. You guys deal with CT cabinet all the time. The reason why we use them is what? Because you, in one side, you bring here 6 runs, or say 12 runs for your 4,000 amp switch gear here, or 11 runs, and the utility end up being with 7 or 8 runs, right? Did you guys have been in a situation where the utilities have half to 1/3 of what you're bringing? So to do that mismatch between what you're bringing and what utility is bringing, we have the CT cabinet, say size the CT cabinet based on what your size is, and we, the electrical utilities, can bring as many as we want from our side. This is the service, so-called the service point right here. Now we're coming through, these are supposed to be a conduit. Now we brought the now I have 4-wire system coming into service equipment. This is probably should not be a panel, should be switch gear. So here's my switch gear, equipment switch gear, if you guys want to call it, because they don't make panels that high. So here's my switch gear, 4,000 amp, 482.77. That's your service equipment. Does that make sense? Right here, that box is your service equipment. we brought a 4-wire, 3 phases and a neutral to it. The first thing we do when we bring it to the box, if you guys remember, we have to ground. The first thing they do is a 2.0, which is bond the neutral coming to the box to the grounding bar inside your switchgear through the 2.0. That's called 2.0. And if you guys go down to 2.0, it says main bonding jumper. That's called main bonding jumper at the service. And here's how we size it right in here. And we'll talk about this one in a second. So that's my main bonding jumper, bonding the neutral basically to the ground bar inside my switchgear. Any comments, guys, about number 1 is the grounded conductor, the neutral. Number 2.0 is that's my main bonding jumper. The reason why they call it main, because it's at the service. The reason why they call it bonding jumper, because it's bonding the system grounding. Remember, I grounded the system to the equipment grounding, right? This is the neutral is actually bringing the system that we already grounded there to the equipment that already here that we are grounding. Does that make sense? Here's the system, here's the equipment. Now we're going to tie them together with the main bonding jumper at the service. Any comments, guys? Does it make sense? Yes, no? So that's my main bonding jumper. By the way, anything that you see green has to do with grounding or bonding. Any color that you have see green is grounding and bonding. Now, right at the service from the get-go, you have to establish to take a wire. This is 3.0. That wire is called grounding electrode conductor. So if you guys go down here to 3.0, it's grounding electrode conductor at the service. Grounding electrode conductor at the service. Now, there's a bunch of description about this right in here, how to do it and how to size it and so forth right here from the NEC code book. And these are all the references that's coming from the NEC code book where this information has been taken, summarizing it. Okay, so now we are at the service. We have a grounding electrode conductor going to, this is a grounding bar. You guys have seen it. I'll have a couple of pictures of these. What typically in a bigger building, they have a copper grounding bar right in the electrical room, and they bring all the grounding electrode system to that copper bar at the basement, typically in the basement, a couple of feet with a couple of inches wide. And you land your grounding electrode conductor here, that's 3.0. Then all these junk here supposed to represent all approved grounding electrode systems by the NEC code book. And I should have named them for you, but you can imagine this, starting from this is a grounding plate, looks like a plate here, that one. This is a grounding, supposed to be a grounding ring. And the NEC code book talk about how to establish a grounding ring, guys. Grounding rod is supposed to be somewhere here. Grounding rod. This is grounding steel of the building. The steel of the building or concrete encased electrode. This is so grounding rod. This is grounding the water. This is if you have a big fat tank in the ground. The NEC code book approved to metallic tank, approved it. You can tie to it to establish so-called the grounding electrode system. So these are all approved method of so-called grounding electrode system, grounding electrode system. The NEC code book says you only need one. You only need one. But if any of these approved method exists inside your building, you're supposed to tie to them. So if your building is steel, all what you have to do is take one wire, number 3.0, tie it to the steel of the building, size appropriately like we showed, and then you're done. Except if you have a metallic water coming to your building, you have to also tie to it. If you happen to have a big tank sitting outside underground, you have to tie to it. If you what else? If your building is if you have concrete encased electrode beams, and building is concrete also, the concrete beams you're supposed to tie to it. So, but you only need one. So we end up being engineered project guys. We end up tying to at least 2 or 3 of them. And sometimes we drive a ground. We have a copper wire around the whole building. We call it ground ring, so we can establish a great grounding electrode system. That will between what you do here and what the utility have done here, that's kind of the tie, almost a tie together. And we don't also depend, can you guys see, here's tying to the ground here, and also we're tying to the ground here. So now the two systems are tied to the ground tied together through the ground as well as through the neutral conductor. Can you guys see that the neutral also acting as bonding between the system and the equipment, right? Because I'm bonding this to this. If you come from here, go through here into the main bonding jumper, into the neutral, all the way to the ground again. It's like parallel path. Any comments, guys, about the 3.0, the grounding electrode conductor, grounding electrode conductors, grounding electrode conductors? So these are, a lot of you are familiar with these a lot because engineers do them all the time. Main bonding jumper, they're called main bonding jumper. Why main? Because it's right at the main. Then there's one little number 4.0. 4.0 is very important. Now you came from the bottom of the switch gear. You can see with 4,000 amp and 3200 switch gears, right? Switch gears are open bottom. So when you bring your rigid conduits, if you're using rigid, if you're using PVC, number 4 does not exist. Number 4 only bonding the conduits, bringing the power into the switch gear at the service. And the NEC code book came up with a name for it, believe it or not. They called it supply side bonding jumper. So if you guys go to all the way to 4 at the bottom here, here's the name of 4. It's a supply side bonding jumper, SSBJ. That's the term that used in the NEC code book for it. And if you guys are doubting Thomas and you don't believe Chad, it's 250.102C. That's where you get this definition directly from there. And how do you size it? You go to table 250.66. We'll talk about sizing there. Now, what is now you brought how many runs did we bring for that one? I mean 10. Okay, so now I have a 4,000 amp. I have a 4,000 amp service coming to the bottom of my switch gear. I want to carry it with 10 runs of 600 kcm, 10 sets of 600 kcm. So imagine 4 or 5 inch rigid conduits coming, if they're rigid, could be PVC, coming from the bottom, inside the bottom of that switch gear, sitting in the bottom of your switch gear. These have to be tied to the frame of the switch gear. How are you going to tie them? You're going to tie them with a wire that's called supply side bonding jumper. Supply side bonding jumper. So that wire, which is number 4, again, it's called supply side bonding jumper. Supply side bonding jumper. I can't emphasize. Can you guys see what I said right here? If you go read through it, it's in the NEC code book. You size it exactly like the main bonding jumper. Exactly like the main bonding jumper. Exactly like the main bonding jumper. So here's my then here's my supply side bonding jumper. I don't know how many of you guys have dealt with it. A lot of us and engineers might not deal with it because electrical contractors, when they walk in, ultimately they have to do the grounding and bonding. But it's really nice for us to know that there is a wire that must come from the service, tie all these service conduits into the equipment. If your service is 225 amp panel, if you guys use the smaller things, 225 amp panel, then that wire might not exist. So if you have a wire hop coming with a rigid, that wire does not exist. The conduit already attached to the box with an approved hand, with approved ways. So that wire might not exist. Notoriously famous, it exists if you have a switchgear or switchboard arrangement and you're coming from the bottom of that switchgear. You always use it. If you're coming from the top of the switchgear with an EMT conduit, you also bond these conduits with a bonding bushing. You put a bonding bushing with a wire and you tie it to the ground bar. Any comments, guys, about 4.0, that supply side bonding jumper? Why do they call this supply? Anybody wonder why bonding jumper? Because it bonds the conduits bringing the service into the equipment frame, the box that the service is. That's where the bonding jumper. Why supply side? Because inside this switch gear, you're going to have your 4,000 amp draw out power circuit breaker, right? And these typically, the number 4 right here is on the circuit breaker sitting here, and the conduit's coming to the line side of the circuit breaker here. So that's where the line supply side, because it's supplying the service disconnect means. The service disconnect means. Any comments, guys? Any comments? Any questions about that? That's right. That's bonding and grounding at this. We're still at the service. We haven't left the service yet. So, Okay, now, still at the service, what I did, any question before I move the service? Now I brought a 4-wire system into my switchgear 4000 amp. I want to take chunks of load from, like we did in the calculation, 2 times for you guys. I'm going to take chunks of loads and go throw them into the building or other buildings and do grounding and bonding too. Again, the focus here is grounding and bonding. So what I did, guys, I have 3 scenarios, actually 4 scenarios for you, based on grounding and bonding, not based on anything else. Scenario number 1, and I'm going to go over the first scenario. Number 1, it's going to be the generator. Now, what happens if you have a generator, backup generator? And remember, here's my gen, a 1250 kW, 48277, in parallel with my switchgear. Running, it could be 1 generator or it could be 6 generators. It doesn't matter when you do the grounding and bonding. That's scenario number 1. Scenario number 2 is the most common one, is what happens if you have a sub panel. I have a 600 amp panel and I'm taking a feeder. In this case, I have a 1000 amp panel. I have a 4000 amp switchgear here. I took a feeder 1000 amp panel and went to the other end of the building and I landed on into another switchgear. Cool. That's called, and also this should be switch. This really panel board, they don't make them, so this should be switchboard. Yeah, I guess you can go also call it switchboard or panel board. 1000 amp, they make a 1200 panel board, so that could be switchboard or panel board. So that's scenario number 1. Now, if you go to, we'll talk about this in a second. Then scenario number 2. Scenario number 3. What happens if you take another 1000? Are we taking another 2000 amp from the switchgear, the 4000 amp here, and went right into that building, right across the streets all the way there, and fit that building, right? That's another sub panel, except the only difference between them is one inside the building, the other one is way completely in a complete standalone structure or building. Why did we get this one? Because every time you take a feeder outside the building to another building, there is a new requirement for grounding and bonding. Does that make sense? So that's a scenario number 3. And the last scenario is also another common one. Now, what happened if you took a feeder to a transformer sitting here and transferred the voltage from 480 to 28120, right? And fed all your receptacles that we burn our receptacles in the US at 120 208, right? So that's so-called separately derived system through a transformer here. This one is separately derived system or non-separately derived system through a generator. Any comments, guys, about these 4 scenarios that I ran for you from this switch here? I believe these guys will cover everything in the grounding and bonding, except DC grounding and bonding is not covered here, and high voltage. Other than DC and high voltage, if you have a 600 volt DC line, or if you have 13-8 system, these are not in this scenario. Other than these, everything basically is covered in that, related to the AC 600 volt or less. Any comments, guys, before I go into each one of these scenarios? Make sense? Too much? Too little? No? Do you guys, every engineering firm that I worked for, they always have a grounding and bonding detail that they send to the customers. And I'm sure a lot of them the reason why this they wouldn't send this to the owner. This is meant for explanation and colored and all the stuff. But I hope the idea behind it is just to throw an idea where these stuff are coming from and what do they mean. Comments, questions? Is it too interesting, too not interesting, too, no? Cool? Okay. Okay, now we did, just very quick, we brought the grounded conductor, the neutral. We bonded the neutral at the service. I'm sorry, did you? This is like an auction. You raise your hand, you buy. So we brought the neutral here. We grounded the neutral to establish the system and the equipment tie. Then we grounded the equipment through all this bar here and grounding electrode systems. Cool? Now we're going to get out of the main panel and go somewhere else in the building. So let's take the first scenario, guys. Going out of this panel, I'm going to go feed a 1000 amp panel. And by the way, if you never dealt with 1000 amp, say, Chad, the highest I dealt with, you guys are engineering firms, I know you dealt with this, but if you deal with only 225 amp panel, it wouldn't be the same. The whole rules will be the same. The only difference would be the size will be different. Other than that, the same rules apply. So for all practical reasons, this panel could be 60 amp panel or a 1000 amp panel, and what I'm saying right now is the same. Size is going to be different. Okay, now I brought a feeder from the switchgear, a 1000 amp feeder, into this sub panel in the same building, right? A switchboard in the same building. Cool. Now this is a 4-wire system, so I brought phase A, phase A, B, C, and a neutral. With phase A and B and neutral, I have to bring something called equipment grounding conductor. So can you guys see 6.0 here, the green conductor? That's called system. That's called equipment grounding conductor. Now, the NDC code book allow you to, if you're using PVC, then you have to put an equipment grounding conductor. No choice. If your feeders were MC cable, if you want to carry with MC cable guys can go as high, I believe, up to 2000 volt, 2000 kcm MC cable. So if you're carrying MC cable, it will be part of the MC cable. If you're using EMT conduit or rigid or intermediate, you have a choice to make. Either you pull an equipment grounding conductor, which is a good idea at this level, or you depend on the conduit to act as an equipment grounding conductor with approval from the NDC code book. Cool. So I got my 6.0. 6.0. It's called right in here, right at the bottom. It says equipment grounding conductor. Here's where we size it, 250.122 right here, and based on the overcome protection device. And if you parallel, they have to go one full set in every run that you parallel. So that's my equipment grounding conductor. The job of the equipment grounding conductor, guys, to take this box here that you're looking at right here and bond it and ground it to this box, right? That's what the job of the equipment grounding conductor. So that you're very familiar with, you do it all the time. When you bring a phase A, neutral, and ground to this fixture, that's exactly what the green is, the ground, the equipment. The technical term for it is equipment grounding conductor. Any comments, guys? Any questions? So that's you're familiar with. What you might not be familiar with is, do you see 7.0 here and 7.0 at the top? Now suppose we're coming from the bottom of the switchgear with a rigid or EMT conduit. Say rigid. We're coming from the bottom with a rigid of the switchgear all the way to the switch point somewhere else. Now we have conduits that's not bonded properly connected to the frame. So what we do is we take a little wire here, which is 7.0. This is called equipment bonding jumper load side. Equipment bonding jumper load side. Why equipment? Because it's bonding the conduit to the switchgear from one side, and also bonding the conduit to the switchgear from the other side. That's called equipment bonding jumper. So if you guys go to 7, tell you how 7 is called equipment bonding jumper load side, and it's sized exactly as what? As the equipment grounding conductor. So what a lot of electrical contractors do, and you probably have seen it all the time, is they bring the equipment grounding conductor, that number 6, they tie it to a bonding lug, a bonding bushing, and they loop it. They get rid of the insulation, tie it to the bonding bushing, and from the bonding bushing continue all the way. So they use 6 and 7, they group them in one conductor to save money. So that's number 7, and number 6 could be one conductor, as long as you land this conductor into with a bonding bushing, tie it to the conduit from one side. Actually, all what you need is one side, but a good idea to put them in both sides because they will act as an equipment grounding conductor if you have a ground fault. And tie them to see how that conduit is coming to tied to the other side. Now, if you have if this panel, guys, is 225 amp panel, if you're coming from the bottom of that panel or the top, the bond, there are multiple ways of doing it. You don't need a wire. So you can have, if your system is 48277, all what you have to do at the end of the conduit, you have bonding bushing, and you tie the conduit directly into the grounding bar inside that panel. If your system is 28120, if you haven't seen it in 28120, there is no need to do anything. That lock nuts that you have in the EMT conduits will act as bonding the conduit to the box. Bonding the conduit to the box. So there's a few ways of doing this without putting a wire. there. Any comments, guys, about 7.0 and 6.0? Going to that panel, 7.0 and 6.0. So that's bonding at the same building. Now I'm going to go right underneath it and do the same thing. Now I took 2000 amp feeder and I went across the street from here and fed another building. So in a case like this, this is a second building here. The only difference, guys, when you have a second building, a feeder feeding at a stand-alone structure or building, the NEC could book treat it like a service. Exactly like you're bringing a service to a second building. So what do? You have to go establish grounding electrode system. Does that look, the ground bar here, the ground bar look familiar? Yeah, exactly, because they are actually the same. They're the same concept. So you go to the second building. You have to have, in the second building, take a grounding electrode conductor called 3.2. I call it 3.2 because it's a second building. Grounding electrode conductor. Tie it to a ground bar if your system is big. If your system is small, you can just take that wire, tie it to the steel of that building and call it a day. You can also, if in the second building, any of these grounding electrode system, if exist in the second building, must be tied to, exactly like if you're bringing a service to the second building. You have to bring an equipment grounding conductor 6.0 that's based on the overcome protection device that's feeding this building. You also have to bond the conduit. If it's metallic conduit, you have to bond the conduit into the grounding bar inside this switchgear or panel board, exactly like if it was in the same building, like we did here. And of course, you have to bring 1.2, the neutral for that building. What's missing here, guys, is do you see any tie between the neutral and the ground in the sub panels, the same building here or other building? You are not allowed to tie the neutral to the ground downstream. You only tie the ground to the neutral right at the surface, right? We all know that, and that's kind of grounded in our minds. Any comments about grounding and bonding at the server, at the separate building, inside the panel, inside the building, or outside the building? Inside the building or outside? Yes, sir. There is an exception. Now you have a garage, a detached garage. If you have a one branch circuit going there, there's an exception. You do not have to establish a grounding electrode system to that structure. That's an exception. If you take a panel, the minute that you start dealing with panels, feeders. If you take a feeder, you have to bond. If you take one branch circuit, you have a detached garage or a detached building, and you take a multi-wire branch circuit, phase A, base C, and a neutral. That's also one branch circuit. Goes 3 phases, still one multi-wire branch circuit. Take it to that structure. You do not need to do, you still have to have a disconnect there for all these. That's a whole different story, but you do not need to do a grounding electrode system and bond and do. Only if you have a feeder. Make sense? Any comments, guys? Any questions about the second building?
You had mentioned that if those grounding types are available, that you have to use them. Is there a specific definition of available? Like if there's very large existing buildings?
Okay, here's... Yeah, go ahead.
Like for like a very large existing building where the water main coming in was at one end of the building, and it was from the entry point from there on, it was PVC or PEX throughout the rest of the facility, and having a service
At the other end.
Is that considered available?
Is it one structure with one service?
Multiple services.
Multiple service coming to the same structure? You're supposed to bond them together. Now here's the deal. If your building is steel, especially if you're building a steel building, you can bond to the north side of the building, and the steel will act as your water will be bonded. You bond your water to the steel on this side and your service to the steel on the other side, and that's acceptable way if it's a steel building. But you need to tie the two ground electrode systems together. So now, would the inspector make you to do it or not? That's a whole different story. But you're supposed to, if it's one structure, fit from one building, fit from one service or multiple service feeding. The reason why you're allowed to do multiple service because of the size is big. You're supposed to tie it to every existing ground electrode system. Because here's the why. Now imagine that north side that has the water there. Imagine are you taking a feeder or branch circuit to that section? You take it there. Now here's the water sitting at one voltage level, and here's a fixture right next to the water line sitting at a different voltage level. It could be hazard. You could live for 150 years and nothing will happen, but it could be hazard. So you have to bond them together. So minimum, you have to have one grounding electrode system, typically the steel of the building or concrete encased rebars, the foundations, if it's concrete building that has rebars on it, that's good enough. One is good enough. What we end up being as engineers, we never go more than one, right? You always drive a couple of ground rods. The code says minimum. We've seen building where they have a 500 kcm copper ground ring around the whole building. And from every side it tied to the rebars of the concrete building or the steel if it's a steel building, and then the whole service is bonded together. Then you can tie to anywhere in the service, and you have the same potential. So, any comments, guys? Thank you. Thank you. If your only grounding electrode system is a water or ground rod, you have to supplement it by another. So you walk into a building, and your building is a wood building, and the only thing metallic in that wood building, no foundation, nothing, is water coming to it. You tie to the water. Then the code says the water is not a reliable source of grounding electrode system. You have to supplement it by a rod. If you walk into a building and there's no metallic water coming to the building, you have to drive one ground rod. So now what are you going to do? Because there's no reliable water, you can drive another ground rod at least, I believe, 6 feet away, and you tie them together, and that's on his two rods supplementing each other. That's for reliability, absolutely. Thank you, Dave. That's if your system typically having a lot, if you have a wood building, wood structure. So you have to, that's why in dwellings you end up with what? Two, a rod and a water pipe. They're supplementing each other. So, any comments, guys? Any questions about that? Comments, questions? So that's my grounding at the second building. I'm sure you guys do the same thing. As long as we're in the second building, there's another thing required in the second building is a disconnect for the building you're familiar with. So I can't take a feeder and go land it into a panel that does not have a main disconnect, main lugs only panel. If you ever have a main lugs only in a second building, you can't land the feeder on the main lugs only panel if it's in the second building. You have to have a main circuit breaker in a second building, and that circuit breaker have to be bolted to the a main has to be bolted to the equipment, not plugged in. So it's like a service. The service circuit breaker have to be bolted in. It can't be plugged in. So that's related to the overcome protection device.
That secondary building has to be service entrance rated as well. It's more than a multi.
Service entrance rated, as in the circuit breaker have to be bolted. That's what service entrance, meaning you can't have a plug-in. You know what I mean? You know, the ones that you plug them in, circuit breaker does not. It has to be this building disconnect with main circuit. But you don't have to bond the neutral to service rated means also you have to bond the neutral with the ground. That's not true in a second building. There are exceptions for this, but you guys don't do existing building, do you? For existing buildings, there's some exception where if this is an existing building and there is no, if an existing building, I hate to go there, this is an existing building and there no metallic object goes from building A to building B at all, including a barbed wire, a heating cooling duct, coaxial cable, a phone line. All these are metallic. If there's nothing between these two buildings, from a phone line into a copper water pipe into anything, nothing metallic tie the two together, and it's existing building, they allow you to bond the neutral and the ground right at the second building. That's exception, and I don't like to mention it to, yeah. Well, yeah, it's because in the future you get a coaxial cable, tie the two together, and your coaxial cable is carrying 5 amps, the shield. right? Any comments, guys, about grounding a second building? Grounding, it's the reason why I picked it up again, because it's a special. And if you go 3.2 here, this is 3.2 grounding electrode conductor, separately building, and I added all these code requirement why it tells you what you have to do, what you have to do here. So that's basically the second grounding and bonding. Sub panels, one in the same building, one in another building. Okay, they're picked because they're unique. Now let's go to the second, to that one. Now, what happens if you have so-called separated drive system? The NEC code book, guys, use a term separated drive system. The way I explain separated drive system is your wiring system on the primary side of the transformer, and here's your wiring system on the secondary side of the transformer, and in between them, electromagnetic field that tie this wiring system to this wiring system. No wire is touching the other wire. That's what separated drive system is. You bring four wires to the transformer from this side, phase A, phase B, phase C. You take out of this system four wires or three wires, actually three wires, here phase A, B, and C, typically. You take four wires, A, B, and C, and a neutral. From the other side of the transformer, in between them, they are electromagnetically coupled together, and there is no wire whatsoever tied the two primary and secondary of the transformer, right? You tie one phase to the other phase, or one neutral to the other neutral, now they are no longer a separated drive system. So I can have a delta separated drive system, delta delta, or delta Y separated drive system, or Y delta. It doesn't matter what the configuration is, as long as you don't tie together. The only thing guys can tie the two together is so-called equivalent grounding conductor and bonding. The bonding conductor is okay. The conduits and the wires, they have to be tied together. But the phases and the neutral wires are completely isolated from each other. So that's your separated drive system and transformer. The reason why you use a separated drive system in the US, why, right? Because we burn our receptacles at 120. By the way, in a lot of parts of the world, like I said last time, 80% of the world use 220, 380, or 230, or 240, and they go 400 or 415. So it's only us, we burn, and a few other countries burn the receptacles at 120. So you wouldn't see this in a lot of application where they burn the receptacles at 220. Okay, now, coming here, this is very typical application, and correct me if I'm wrong, guys. You come with 3-wire delta 480 to a transformer. You come out with a 4-wire. They're color coded based on industry standard. You can see the color coded the 28120. Now you created a so-called, can you guys see the wires here and the wires here? They're not touching each other in any way, shape, or form. Exclude the green. Don't look at the green. The other colors, are they touching each other? That's where your separated drive system is. So you come up here. So now the first thing you need to do, since you created a neutral, you have to establish reference to the ground for the newly established neutral, right? I created my neutral here. The only reason why, so then I have to bond the neutral. First, I have to have a ground, take that transformer and take it, or establish a ground this box, or sometimes this box, all the way back to the ground bar or grounding electrode. Can you guys see a 3.1? That's taking your ground, your separated drive system transformer that you own and operate, take a grounding electrode conductor all the way back to the ground bar inside your building, or to the steel of the building. Doesn't have to be really going all the way back here. It could go to the steel, rebar or steel in your building. So that's, this 3.1 is grounding the equipment here, the separated drive equipment. Any comments, guys? Does it sound like a service? Exactly. Separated drive system sound exactly like a service. As, right? Isn't that what we did here? We called it 3.1. That's why I call it 3. The 3 are grounding electrode conductor. 3.1 at the service, 3.0 at the service, and 3.1 is at the separated drive system transformer. Okay? Now, if you guys go to 3.1 here, that's why I call it 3.1 right in here. 3.1, it says grounding electrode conductor underneath the separated drive system. That's how you do it at the separated drive system. Okay, now, and how we size it. Now we come over here, then, do you guys remember that conduit? That conduit that bringing the wire to the transformer to? You have to bond the conduit to the frame of the transformer. with a tiny little wire called 7.0. Does that sound familiar? That's called equipment bonding jumper load side. Load side, right in here. We're on the primary side, load side. And if you go 7.0, right in here, here's your 7.0. And for the transformer, here's for the transformer, the size is number 6. We'll go over the sizes in a few seconds here. Okay, then I have to also bring an equipment grounding conductor. Can you guys see that 6.0 here? I have to bring an equipment grounding conductor with the conduit if it's PVC, all the way to the transformer. That's grounding the frame of the transformer on the primary. We're still on the primary side. So exactly like if the transformer was a panel, you have to bring an equipment grounding conductor. What they typically guys do, they bring the equipment grounding conductor, they tie it to a grounding lug there, bushing, right? And then they tie it to the ground bar, to the XO or ground bar inside the transformer. Then you have to tie your neutral, the XO of the transformer, that's a neutral point, into the grounding bar inside your transformer. You have a lug and you tie all of them together inside the transformer enclosure. But what you do is you establish the neutral have to be grounded or tied to the grounding electrode system inside the transformer. This is called 5.0. If you guys go to 5.0, and 5.0 is nothing but it's called system bonding jumper. This is your system bonding jumper. For all practical reasons and sizing, system bonding jumper and main bonding jumper are identical in operation and function and sizing. We size them exactly the same, as in the same way, not the same size, the same way. So if you guys look at 5.0, it's size, here's where it tells you to size them, but we size it based on the conductor coming out of the transformer from table 250.66. So that's where you hear the word system bonding jumper, system bonding jumper versus main bonding. Do you guys remember that main bonding jumper 2.0? That's if you put it here, it's main. If you put it at the transformer, it's called system. Identical operation and function, an identical sizing way. I can't emphasize that one because it used to drive me nuts years ago. So that's your 4. Then 1.1, guys, this is your neutral that you pull. That's your 120 neutral. You pull it all the way. Now that you move to you move the 4-wire system into the panel. Now you have to pull 4.1. I call it 4.1 here. 4.1. If you guys go to 4.1, 4 is supply side bonding jumper. If you look at the supply side bonding jumper, guys, let's look at the 4 first. This one is supposed to be a 4. Where's my 4? Here. That conductor. I'm sorry. I think I screwed up for you guys here with something. Can you point to this one here? This is supposed to be. I don't know what happened here. Paste. Oh boy, that's interesting. Okay. Can you guys? I'm modifying it as I go here. This number here should be 4. Right in here, that conductor, and I'm going to get rid of this right in here. That conductor should be, can you guys adjust that? Right here. That one is called 4. All right. Apologize for that one. So this conductor is 4. If you go look at 4, this is supply side bonding jumper. Supply side bonding jumper, supply side bonding jumper, and I know supply side bonding jumper, and 4.1 also 4.1 also supply side bonding jumper. I think that's what I did. Also sized like the supply side bonding jumper. 4.1, where am I here? 4.1 supply side bonding jumper. Oh, supply side separately derived system. Supply side bonding jumper, separately derived system. Yeah, they're the same sizing, but you can use them either or. That's why. Oops, let me go here. Okay, so you can either or. You can use 4.1, which is bonding the conduit from both sides. It will act as your supply side bonding jumper, or you can pull a 4 Number 4, which is a wire inside the conduit. In either way, though, if you pull the wire, you still have to put the little dot here and bond the conduit. That acts as your supply side bonding jumper. Supply side bonding jumper. Any comments, guys? Any questions about the supply side bonding jumper? Supply side bonding jumper. Either you bring a little wire here to the conduit, the same thing to the conduit, so the conduits acts your supply side bonding jumper, or you can bring a conductor inside the conduit, tie it from one side to this side of the conduit, tie it from the other side to the other side of the conduit, and continue to tie it to the ground bar inside the panel. Yes, absolutely. Now you could take that wire here and tie in the new bond right at inside the panel. Absolutely. Bond inside the panel. You bond at the location of the first over the line side of the first overcome protection device. The line side. Now the line side could be inside the panel here or anywhere from the transformer into the panel, because that's the line side. You're bonding at the code says the line side of the overcome protection device for a separate drive system. So the overcome protection device is going to be inside that panel, right? Now you can bond right inside this transformer or right inside this panel, but not both though. But not both. Do you guys bond inside the panels? Do you bind inside the panels? Yeah, which is absolutely correct. If you bond inside the panel, if you your equipment grounded conductor that comes from here to here, that's still supply side bonding jumper. It's not an equipment grounded conductor. That wire here, that one. From the transformer into the panel, you need an equipment. You need a conductor for the ground. That conductor is called supply side bonding jumper. Why supply side? Because the overcome protection device for the separate drive system is sitting here. So anything on the line side, exactly like at the main, identical to the main. And that was changed in 2011, guys. They brought with the naming business. Anything on the line side is called supply side bonding jumper. What the difference is, the way we size it though. If it's supply side bonding jumper, then if you guys look at 4, you have to size it based on 250.66, exactly like the system bonding jumper. If it's equipment grounded conductor, you have to size it based on 250.122. 250.122. Any comments, guys, about grounding and bonding at the separate drive system? So you're allowed to ground and bond at the separate drive system. You have to the most common thing is to have to grab a grounding electrode conductor and go all the way to the closest grounding electrode system in your building and tie to it. Tie to it. Any comments, any questions, corrections? No? So that's my grounding and bonding at the service. At the separate drive system. I'm gonna go back to the generator. Any question, guys? Dave, any comments about that one? Correction, please feel free. I mean, it's anything that you guys do different. Or anybody? I didn't mean to put you on a spot or anything, but that's purely my understanding. The supply side bonding jumper is confusing. Came in 2011. In the past, they used to call it equipment bonding jumper line side. If you guys are familiar with the equipment, it used to be equipment bonding jumper line side, and it confused the people. So in 2011, code 2011, they changed it into supply side bonding jumper. And you can use it in 2 locations, at the service and at the separated drive, every separated drive system. The last thing I want to mention, guys, before I show you the calculation, and feel free to adjust the calculation, generators. Now we have a generator. For generators, you have a major decision to decide. Am I going to run my generator separately derived system, or am I going to run a non-separately derived system? For the transformers, we have no choice. Do we have choice for transformers? 480, 277, 480 primary, 28, 120? Does any one of you guys decide, I don't want to run a separately derived system? Well, how are you going to come up with a neutral then? Yeah, you have to, for transformers, you have no choice. You have to run a separately derived system. For generators, you have a choice. For generators, your choice would be, would you like to, since the voltage on the generator and the service are, the problem with the receptacle panels and receptacle transformer, the voltage are different, so you have no choice. You have two different neutrals at two different levels. You can't tie them together. So the generator voltage is the same and the service at the same, so you can't tie them together. You make a decision. Either I'm going to tie the neutral together and use them, bond them together, and then I'm running a non-separately derived system, or I'm going to separate them and run a separately derived system. That's where it becomes a major decision that you have to make on the generator. The difference would be are you installing a 4-pole auto transfer switch or a 3-pole auto transfer switch? A lot of people use a 3-pole auto transfer switch cheaper, so they run a non-separately derived system. If you have a paralink switch gear, you typically are going to run a non-separately derived system, 3-pole circuit breakers, and you tie the neutral together, all the generators together. So this particular one, we decided to run a non-separately derived system. By the way, I'll tell you if it's, I'm sorry, this is a separately derived system. The difference is, can you guys see that little deal, that green thing here? You can just remove that green and the system becomes a non-separately derived system. That here. So I have a separately derived system. I bonded my neutral at the ground inside the generator. You have to bond it inside the generator, the neutral, the ground. This is called 5.0. If you guys remember, 5.0 was called main bonding, system bonding jumper right here. System bonding jumper at the generator. That's how we size it. We'll talk about this one in a second. So the first thing you do when you have a generator, we're running a separately derived system. I need to bond my neutral to the ground inside the generator. I bond them together. I have a 4-wire system coming out of this generator. 480, 277. Then I also, for the generator, I need to, since it's separately derived system, I need to take a wire 3.0, since it's separately derived system, and take it to the grounding electrode system, in your building. So that wire can go all the way, if it's a major building and you have a ground bar as a reference for all your grounds, you can take a wire 3.0 and tie the ground and the neutral inside the generator all the way to the grounding electrode system in your building. Or it could be if it's outdoor, it could be a driven a rod. You drive right by the generator and you bond the ground rod into the neutral and the ground inside that generator. Does that make sense? Taking the 3.1, this is called grounding electrode conductor, going all the way back for the separately derived system. The second thing you do is 4.2. 4.2 here, 4.2, if you guys go to 4.2, 4.2, I call it supply side bonding jumper separately derived system. I researched it, Dave. If your system is also non-separately derived system, that wire still continue to be a supply side bonding jumper. So it's called non-separately derived generator or separately derived generator. Either way, that wire here, right in here, that you bring through your PVC conduit. Say if you are bringing a PVC conduit, you bring a wire through it, that wire all the way to the circuit breaker, all the way to that circuit breaker. So your circuit breaker in this case will be located right in, that's a confusing part. Your circuit breaker is going to be located right in here. That wire comes all the way to the enclosure of your circuit breaker. That's called supply side bonding jumper. If your circuit breaker is located on the generator, like a lot of them are, you have a circuit breaker disconnect on the generator, then that wire comes from the windings all the way to the frame of the generator. The wire that comes out of the generator enclosure all the way to the panel, that's called the grounded conductor. I can't emphasize that. 4.2 is actually the wire coming to wherever the enclosure of the circuit breaker is located. If your enclosure is located as part of your generator, then that's part, everything is bonded inside the generator. Then you take a wire from where your circuit breaker on the generator located all the way back to the panel or to the auto transfer switch. That wire, after you go through the circuit breaker at the generator, the wire downstream becomes equivalent grounding conductor. Very, very clear. So these are typically, guys, if you have a parallel switchgear, you deal with parallel switchgear, you take your power out of these beasts, 1250 kW, in a conduit, and you land them into a parallel switchgear, and your first circuit breaker will be located inside the switchgear, right? Draw-out switchgear. If you have a smaller generator, emergency generator sitting there, your circuit breaker disconnected will be located right at that generator, right? In a case like this, that 4.2, it's going to be called equipment grounding conductor. Equipment grounding conductor. Any comments, guys, about 4.2? In this case, it's supply side bonding jumper. Regardless if you're running your generator separately derived system or non-separately derived system, it doesn't matter. That 4.2, as long as it lands here, your circuit breaker is landing in here, 4.2 continue to be supply side bonding jumper. The minute that you put your circuit breaker from here, now from here down, that becomes equivalent grounding conductor, regardless if your generator is called separately derived system or non-separately derived system. Any comments, guys? Any questions? Since this is separately derived system now, when I land them into my switch gear, either I have to have a 4-pole circuit breakers or a 4-pole auto transfer switches, right? To transfer the neutral as well as the 3 phases. The same thing, guys, the only thing would change if this was a non-separately derived system. The only thing that would change is that number 5 no longer exists. If it's a non-separately derived system, that number 5 wire no longer exists. Everything continues to be the same. Any comments, guys? Any questions? Corrections? So that's kind of I thought, do you guys think of any scenarios there that's not here commonly used other than DC and high voltage? Do you guys encounter any scenarios that's not here? There's scenarios where you can bond, there's a lot of other bonding that we use. It's HVAC equipment. The grid here has to be bonded. But these we bond them based on the closest overcompression device to them. So, if I have... Yeah, equipment bonding. Absolutely. Yeah. Yeah. Water meter. Yeah. Yeah, part of your grounding electrode. Yeah. Yeah. And I always wonder, Dave and everybody else, is like if you bond the pipe of the gas at the top, well, how about the bottom? That's what's coming underground. I believe they have insulation inside the meter somehow, because if it's all metallic and you bring so it's called equipment bonding jumper, that one. Equipment bonding jumper to the gas line above the ground, the gas line under the ground, which is you're prohibited from using it. They're tied together through their meter, but I think they have insulation somehow through their meter. But never bothered me to do it. It's underground. Yeah, they don't want you to tie to the underground. I have one. I have a picture right now. I'm going to show it too. I have a picture right now. I'll show it. So I don't want to walk you guys through the whole thing, but feel free to look at how they're all sized. I'm going to walk you just through number one. If you look at grounded conductor, how we size the grounded conductor, I think I grounded conductor, the first one. The NEC code book says we size the neutral three ways last time. Here's another way at the service that you cannot go below. The NEC code book guys can say that the neutral under no circumstances can be smaller than the main bonding jumper. So I use this one at the service. So here's my main bonding jumper. I carried 600 kcm for the service, right? 600 runs multiplied by 10 based on 250.28D1. It tells you if you are higher than 1100 kcm, then you have to take the number of runs, which is 10, multiplied by how many conductors you're running for the 4000 amp switchgear, 600 kcm, multiplied by 12.5%. That will give you 750 kcm. That's your neutral size. Then you divide the 750 kcm. If you go to table, this is the main bonding jumper, yeah. That will give you, actually it is a size 700 kcm. That's the main bonding jumper. So your main bonding jumper at the service is 750 kcm. I want to let you know, if you have a switchgear, you would never see a wire that size, guys. What they do is they have a cover bar that ties the neutral and the ground together. I have a picture of it later. In a second, I'll show you. Now that's the main bonding jumper. The grounded conductor, the neutral, same thing. You take the 750 here, the I size the main bonding divided by 10, because I have 10 runs of them, right? Because it cannot be less than the main bonding jumper. That's my minimum. And either you do the calculation that I did last time for the neutral, or this is an alternative way. So that will give you 750 kc, 75 kcm. From chapter 9 table 8 give you number 1. I want to warn you that you cannot parallel less than 1 aught anyway. So in a 4000 amp switch gear, the minimum in neutral grounded conductor that you can put has to be 1 aught, but they have 10 of them though, one with each set. Now I know when we did it last time, we came up with a bigger size, guys, based on the 200 amp and so forth. But that's your bare minimum from any secret book. I know engineering firms that they use this one as your bare minimum at the service, and others will use the alternative ways that we did. So that's basically, I thought, and all of them are the same calculation here. Grounded conductor for the generator and so forth. For the grounding electrode conductor, guys, here's all the summary of how to size them. So you can go 10, the same thing, 250 to 66. You don't have, for the grounding electrode conductor, you do not need to go larger than 3 aught. The one that's going to the rod directly doesn't have to be more than number 6. The pipe, number 6. The plate, number 6. The concreting case, number 4. The ground ring, number 2. These are directly from any secret book. If you have a wire going to any of these grounding electrode system, you do not need to. Now we go higher than that as engineers, but that's your bare minimum directly from, if you guys go to 250 to 66, these are all in there. So that's what I thought. I want to just take the equipment grounded conductor, very easy. You take the 200 amp panel, you take the 200 amp to 250.122, give you 250 kcm. That's the equipment grounded conductor that you have to pull with each and every, I can't emphasize this one, when you parallel one full size equipment grounded conductor in each conduit. The rate based on, no, these are equipment grounded conductor, they're not carrying current. We're here at the service. So now you have 4 conductors carrying current in a conduit, and if the neutral is carrying, if your neutral is carrying an unbalanced current between the 3 phases, the code says you don't have to calculate it. Only if it's carrying a harmonics, and at this level, at the 4000 amp level, you can easily consider it an uncarrying conductor. And even if you do, and you do rate, you're going to see that your conductors will be okay. This is the least of your problem. Do you guys remember what we did last time? when we said when you have 10 runs underground. Is there a table in an DC code book can get you 10 runs underground ducts? There's no table. So we talked about amp calc. So that's really, so you have to use an amp calc even for that one. Any comments, guys? Any questions? I appreciate any correction. If you guys go through it, you find something that doesn't make sense. This is purely my understanding. Trying to pull the whole thing together. So I hope that was, if it's a little bit complicated, it is. I mean, that you bring in all the systems together in one sheet. Like I said, we're only missing grounding, missing high voltage and the DC. So with this, I thought if I can get you guys a couple of things, a couple of pictures to see here. Okay, come on, Chad, there you go. We don't have, we lost a few time here. So I'm going to go just a couple of things, talk about grounding. Here's a couple of pictures, guys, about the whole grounding and bonding. I want to throw the terminology that we use. This is grounding electrode conductors. This one right here is the system bonding jumper. And the conduit here is acting as an equivalent ground conductor. Talked about these. Here's the systems that we talked about, grounding the systems versus grounding the ungrounded system. The NDC code book require you guys to have a label if your system is ungrounded, because we got sick of killing electricians trying to, and burning equipment trying to go to a panel looking for neutral that does not exist in a panel. So now you have to have a label right at the service, at the panel, or at the source of the source of the ungrounded system, saying that your system is ungrounded. You also require, if your system is ungrounded, you require to monitor the line to the ground, so so you can alarm if you have a ground fault for reliability reasons. So you can go and assign your maintenance group to go on a Sunday night and fix that problem. So you have to monitor the line to the ground. Here's a grounding system we talked about. Here's an example, guys, of do you use a corner grounded system? That's one of the most weirdest application. No engineer should ever use that. This is where you use a corner grounded system. A corner grounded system, if you have a delta and your delta keep burning, do you guys, have you used a corner grounded? Dave, do you guys use a corner grounded? So you have a delta. Yeah, it comes. This is a solution for a problem. So you have an ungrounded system and there is a transient in your building that keeps burning your VFDs. One solution is to take phase B typically and tie it to the ground. So now you have so-called grounded, corner grounded system. And then you have, this is a grounded conductor. This is so confusing and it will burn a lot of equipment for the maintenance guys, because imagine an electrician walking in here on a panel and looking at this white conductor. This is phase B, and pulling it as a neutral with a phase C and getting 480, or getting two, in this case it will be 480 or 240 system across the equipment and burning them. I have stories to tell about it, but we don't have time. This is just telling you guys the series and parallel path. If you have parallel path for your equipment grounded conductor, it will take each and every path. The code says, guys, at the service, you have to bring your neutral to every service and bond it to the enclosure of that particular service. That's very clear in an EC code book. If you have an impedance grounded system, look how they do it. Here's an example of having an impedance grounded system. Can you guys see where they tie the neutral to the equipment grounding system to the neutral is tied through this impedance? And they do have monitoring system right here that monitors the line to ground voltage or the phase to ground voltage. These are the lights that gives you, in this case, phase C have a ground fault on it because the light dim. You've seen them, or they have electronic equipment to monitor the ground faults. Here's where you're bonding your neutral. Here, a couple of examples. One way of bonding the neutral is to come here, right here, and take your grounding electrode conductor. That's where you ground your neutral. Your system, your equipment tied together through this nut right here. And that's what I like about these. Here's a switch gear. In a switch gear application, your grounding bar typically at the bottom here, and and you tie with either a main bonding jumper or a system bonding jumper. You tie them together. This is actually main bonding jumper at the service. So this is an exception where you don't have to bond at each and every one of these disconnect if you have an assembly. You bond right inside the assembly, and you don't have to bond the neutral to the ground here and here and here and everyone else. You bond it one time. A good example of this one, guys, is meter centers in an apartment. You bond them right in. You don't have to bond it. Here's your main bonding jumper as a screw. It doesn't have to be also a wire. It could be a screw. Here's your main bonding jumper taking your neutral to the ground. Very typical in switch gears application. It's a copper bar. If it's a copper aluminum bar like this, it's sized by UL, and so we don't have to worry about it. The manufacturer will size it for you. So, and anything of 2000 amp or 1000 amp typically is done by the manufacturer. You can take it out if you don't want to bond them, if it's sub panel. This is supply side bonding jumper. These are all rigid metal conduit or EMT coming to the bottom switch gear. That's how you tie them together with a wire knot. You have two options here. You can either daisy chain them, each one of them, and size based on all the conductors together, or you can home run each one of these to the ground bar, and then you size based on the conductor inside this particular conduit, and that makes a big difference in the size. Does that make sense, guys? Daisy chain. These are home runs from each one, or daisy chain them. So here's how you bond. You don't have to also remember that bonding wire that I talked about. There's an alternative for it. You have bonding lock nuts here, or you have bonding wedge that can take advantage of bonding your conduits instead of tying it to a wire. Here's another a threaded. Also, if you have a threaded connectors that or a hop like this, can get you away from bonding the conduit with a wire. That's what we're trying to get into. Here's the most common ones. You come over here, bonding the conduit. Look how they're coming with an equipment. This is a system, a supply side bonding jumper coming in, bonding the conduit and going all the way to the, I assume the neutral part on one side. See how they lube it and they bond it. You probably have seen a few of these. Here's the notorious, the famous bonding bushing, where you can bond the conduit. This will get you equipment bonding jumper or supply side bonding jumper, either one of them. These are a system, the grounding electrode system. I went through tying to the ground, all these tying. Here's what you said. If you have multiple systems coming to the building, you have to establish grounding electrode system around the whole building and tie them all together. So that will get you, you can't just isolate them if they're coming to the same building. This is where you measure the ground, the impedance of the ground. The NDC code book says if it's more than 25, you have to supplement it if it's a rod or ground, but that's, here's where you can see how the services is, multiple services here. You can see the neutrals coming to every service and bonded to the grounding electrode system at the service too. Here's the bar that I was just talking about in multiple buildings. This could be coming from the ground rod or from the steel of the building. This is going to the generator of the service. So you can see a lot of them are, you guys have probably wired a few of them or designed a few of these. You have to bond, if you protect your grounding electrode conductor with a conduit, metallic conduit, you have to bond it too. You guys have seen that one. The code says you have to bond it if it's a grounding electrode conductor. Or as a matter of fact, equipment grounding conductor, you have to bond it too. Here's bonding the conduits at the service. Different ways of bonding at the service. I thought just, and not the service, also a 250. If you have a 250 system, these are the approved. If the voltage to ground is over 250, like 277, if it's 28120, it doesn't matter. Lock nuts will get you there. But that's special for 250. Concentric, eccentric. Here's the bonding, because these are concentric and eccentric knockouts are encountered. You have to supplement the bonding with a bonding jumper. You see them all the time here. Bonding multiple raceways. You can see that. The frame of the building, if it's steel, will act as a grounding electrode conductor, so you don't have to bond them together. This is equipment grounding conductor in parallel. You can see if you have to run a full set of equipment grounding conductor in every single conduit based on the overcome protection device. So I thought that's another example. This is isolated ground system. You guys use them for data center. So you have an isolated ground bar here, and you bring from all these servers, and so forth. You bring them all the way to the isolate, and the code allows you to take them all the way down to the panel for interference and so forth. This is all conductor to be installed together. You have to group them. I'm not going to talk about this one. This is, guys, with based on a short circuit withstand rating, you can oversize the equipment ground conductor. We'll talk about it another. Here's your transformer separate drive system, bonding your neutral into the ground bar, neutral bar to the ground bars. Here's your system bonding jumper where the XO, is it XO or X3? Doesn't. This is my neutral, supposed to be the XO here, tying it to the ground bar that we're just looking at. You guys will see all the time. Inside the transformer here. Here's the same thing inside the transformer. Here's another way of doing it. You can, here's what you said, Dave. You can use the same thing. You can, system bonding jumper can be inside the panel too. So system listed equipment. Here's a ground bar for the high voltage and low voltage inside the equipment. Here's what you mentioned. If you have a riser, you can have a grounding electrode system going all the way up, and you tie into it with irreversible means and tie each and every one of your grounding electrode. Engineers draw this one all the time. If you do it this way, it cannot be less than 3/0 copper or 250 aluminum. That's a riser, grounding riser. If you, yeah. This has to be irreversible means either exothermic welding or crimp. You crimp it, but you can't use split bolt on it. So here's a generator outside. If your generator is separate drive system outside, you have to drive a ground rod next to it as of 2011 and bond the frame or the neutral if it's separate drive system to it, and then you pull a grounding electrode conductor or a supply side bonding jumper or equipment grounding conductor, depending on if you have a circuit breaker here or not. This is the definition of separated drive system. You can see the neutrals are separated here, and then you can bond the neutral to the ground here. This is an unseparated drive system. You can see there is no bonding the neutral to the ground here because the neutral of the generator and the neutral of the service are bonded together. Does that make sense? A couple of these, your generators, permanently installed generators with different. Here's what I mentioned. This is your supply side bonding jumper, guys. There is no overcome protection device. That's called supply side bonding jumper. The minute that you put your overcome protection device right here, this wire turned into an equipment grounding conductor. Very, very clear, the code. What's the difference? The sizing is different. One is based on the circuit breaker, the other one is based on the conductors. This is just telling you grounding at the second building. You have to establish a grounding electrode conductor. Look at the isolation between the ground and the neutral versus here. They're tied together right here. The ground to the frame. Here's isolating the neutral. Here is not isolated because it's sub panel. Objectional current at the second building. This is a ground fault protection. You guys are familiar with that one, 1000 amp 48277. I thought just to throw a monitoring system, relay monitors. Here's another example of a ground fault protection required on every grounded system, solidly grounded system, 1000 amp or more. You have to have a ground fault protection. Since if there's a higher value of a ground fault, it will isolate your system from the danger of high ground faults. Is what happened if you don't have a ground fault protection in your system, and you have a high enough ground fault that burn your equipment but not high to trip the circuit breaker. That's why we have a ground fault protection in them. You guys are very familiar. When we do the overcome protection device, I'm going to be talking about the pickup, ground fault pickup and delay and all these, so it's coming. So bonding, the other thing is, guys, bonding at hazardous location. If you do gas stations, so forth, they do a lot of bonding. Also the conduits. If you do gas station, are you guys in the cow business, residential and building? So they have a whole lot of bonding for number 8 cover for the equipment. You're in the hospitals, right? You do hospitals. So when you do hospitals, you have to have an isolated ground system in the patient areas. And bond everything metallic to it, excluding fixture that's 7.5 feet or higher. So that talks. Here's the healthcare facilities. that we use, you have to have two grounds, one clean, one dirty. Except you have to tie them together at the end, right? At the serve. It's not isolated ground, it's an insulated ground. Reliability is, yeah.
You don't have to use an isolated ground.
Uh, in the patient care areas, you have to have two grounds. One fully insulated ground, and the other one is the shield or another ground, like in this case, two cables. But right at the receptacle in the patient care area, you have to tie that's why it's not isolated. You have to tie the insulated grounding conductor and the dirty conductor together right at the receptacle. It's not really isolated. It's not an isolated ground system. It's an insulated grounding conductor, redundant insulated grounding conductor. It's really not an isolated ground system. Yeah, you're absolutely right. It's you pull them all together, but you have to tie them at the equipment. Yeah, it's not an isolated ground system for data, and then even the data guys don't like it. Yeah. A couple of things, guys, about swimming pool. I'm bundling in with number 8. I thought just to give you in it. This is isolated ground connection. Here's where isolated. Even the data guys say they don't like it. I don't know if you guys use isolate. This is an isolated ground system where you take all your receptacle, tie them together with an isolated ground bar here, and the slots here is completely isolated. There's a triangle that says they are isolated ground receptacles, and you take them. My understanding, they use it for interference here to reduce the interference with electron equipment. But I've been in a couple of training classes where people who do it, they don't like it because it creates other problems. I don't know what you experience, guys, with that. If they ask for an isolated ground system, that's what you're looking at. It's right here, orange triangle at every receptacle, grouping them together inside the panel separately.
The IT guys don't want them on their racks anymore. They'd rather have a standard grounding system.
Then isolated ground receptacle.
Sounds confusing, but that isolated ground is not possible.
No. Yeah, the hospital is really redundancy in the ground. You're absolutely right. Redundancy in the ground. Insulated though. So signal grid, I thought just this is your signal grid where you guys with data center, they have a signal grid underneath the servers and you tie it to the grounding system. Couple of examples of signal grid. There's something called the bonding system. I need to let you go, guys. Inter-system bonding jumper for all the telecommunication equipment have to be tied to it by the code with number 6 conductor right here. Required the electrical contractor to provide it. And then the last thing, guys, is grounding for high voltage through the shield. The shield of the medium voltage have to be grounded to the ground rod to drain the voltage and so forth. And then the lightning is the last thing we do grounding. So we do grounding and bonding, guys, 16 hours. So I did what I can do in 2 hours. Less than 2 hours. You stole 15 minutes of my time. Any comments, guys? Any questions? I hope that will help. If you guys have any correction, please bring me my attention. That's only my understanding based on what I read, and I could be wrong easily. Thank you.
You get an attendance taken after